All right, we're in section 8.3 where we're going to show that a quadrilateral is a parallelogram. So, if you remember from 8.2, we had a definition of a parallelogram where we talked about the different properties. And um, basically, what we said was anytime a quadrilateral is a parallelogram, it means that opposite sides are parallel and opposite um, angles with respect to the diagonal are congruent. Consecutive angles in that case would be supplementary, stuff like that. So, first page here kind of just goes a little bit in depth on the different theorems, basically what we talked about yesterday, and then second page of the notes is just being able to apply it. So first off, we're looking at the first theorem here. We're talking about different more characteristics of parallelograms. It states, the conditional statement states that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So basically what that means is if they're congruent, that also means that they are parallel. So that gives us the distinction there. So we have our if-then statement written here. So they're saying that if AB is congruent to CD and BC is congruent to AD, then ABC is a parallelogram. We look at this theorem here. It says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. We talked about that in 8.2. So if these two here are congruent, so they're saying that the measurement of angle A is equal to the measurement of, or congruent to the measurement of angle C, and also the measurement of B is equal, congruent to the measurement of angle D, ABC is a parallelogram. Here it says if one pair of opposite sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. So they're just looking at one side. So they're saying like, oh, if BC is congruent to AD, but also BC is parallel to AD, then we can say that this figure, this quadrilateral is a parallelogram. The final theorem on this page we have, it says if the diagonals of a quadrilateral bisect one another, then the quadrilateral is a parallelogram. So remember definition of bisecting. It means that it intersects, and where it intersects, it means that it splits it into exactly two parts. So basically what you're having here is the diagonal AC and the diagonal BD, they bisect, which means that the point that I just drew here is the midpoint between AC and BD respectively. So being able to apply these different theorems, what they're going to do is ask you a series of questions similar to this. It says in quadrilateral GHJK, which is located right here, it says that the measurement of G is 55 degrees. I'm just going to write that in. It says H is 125, and it says that J is 55. They want to know what the measurement of angle K is. Well, we know that diagonals had to be congruent, so it has to be congruent with angle H, so that's going to be 125 degrees. And they want to know what theorem that was. Well, if we look back in theorems that talks about opposite angles, and that was theorem 8.8. Here it says they want you to find the value of x, um, and it says that the quadrilateral is a parallelogram. So what it tells us in the directions that it is a parallelogram, that means it possesses all the characteristics of a parallelogram that'll help us solve the problem. So in theorem 8.10, they said that the diagonals intersected, they bisected. So if they bisected, that means that the measurement from here to here is going to be the same, just like these two side lengths, or these two line segments are congruent as well. So since those are going to also be congruent because of that theorem, we can say that 5x will be equal to 2x plus 9. To solve for x, we subtract 2x from both sides. This gives us 3x equals 9. Divide everything by 3. X is also going to be 3. Finally, it says show that quadrilateral KLMN is a parallelogram. So here I gave you the definition of a parallelogram, which means that both pairs of opposite sides are parallel. When you're looking at a coordinate plane such as this, where they give us an ordered pair, the best way to determine if sides are in fact parallel is finding the opposite side's slopes. So if you remember how to find slopes, you could, just count it up, the rise over run on the graph, since we were given a graph. But if you weren't and you were just given a series of ordered pairs, you can use the formula for slope, which is m equals the y2 minus y1 over x2 minus x1. So looking at this, I want to find the slopes between points L and M. So right here to start with. So to do that, slope is going to equal, let's go 0 minus 4 over 6 minus 4. This gives me negative 4 over 2, which when I simplify it, it gives me negative 2. So we found a slope to a line segment LM. Now we have to look at the slope between K and N. Now that one has to be negative 2. If it's not negative 2, that means they're not parallel, and this figure is not a parallelogram. So looking at the slope of this one, I get negative 2 minus 2 divided by 4 minus 2. This gives me negative 4 over 2, which gives me negative 2. Since they are the same, I found at least these two opposite sides are parallel, all right? Now we have to check the other two sides. So let's look at K and L. So that slope is going to be, let's see, what, 4 minus 2 divided by 4 minus 2, which equals 2 over 2, which gives me 1. And then the final one, we're going to look at M and N. So I got M is going to equal, looks like it's going to be 0 minus negative 2 over 6 minus 4 plus plus on this. So I get 2 over 2, which equals 1. These are the same. So I have, by the definition, two sets of opposite parallel sides. So because of this slope value of each of the opposite sides, I can say that yes, K L M N is a parallelogram. And that is being able to show a quadrilateral is a parallelogram. Hope this helps. Till next time.